Event-driven programming and the other techniques that we're going to study in this lecture give us extra flexibility on top of the control structures that we have studied. We have studied a number of control mechanisms, of control structures, the so-called control structures of structured programming. I hope you remember all of them. The compound or sequence, the loop, and the conditional, the if then else, in their various forms. And they're very good. They enable us to write any program that we need to write. But they're also a bit constraining and restrictive because they work best when we can predict in the program in what order instructions are going to be executed. Often that is the case, but not always. There's also a scheme of program execution in which it's the execution itself which determines what's going to happen next in the form of events that occur. We're going to see examples in a moment. So in situations like these, although we could still write everything using standard control structures if we wanted to, it would become a bit heavy and not very convenient, and using event-driven programming is going to give us a much more flexible and elegant structure. This will be even more effective if we can rely on advanced language constructs such as the agents of Eiffel, which are going to provide our basic mechanism. In other languages there are some corresponding techniques. For example, C# has delegates. Functional languages such as Haskell have closures. The general idea is the same. Event-driven programming is one of the applications, and it's the one I'm going to start with, and it is particularly useful in interactive graphical programming, what is known as GUI, graphical user interface programming. That's going to be the basic example, but there are many others. For example, we can program iteration using these techniques. They're also very useful in numerical programming. Say, for example, that you want to write a routine to integrate functions in the mathematical sense of integration. Well, agents and such techniques are going to be very useful for that. There are applications in concurrent programming in many other areas, so it's a set of mechanisms that are very powerful and nicely complement the rest of the object-oriented mechanisms. We start with event-driven programming. To understand event-driven programming, it's good to take a look back. So this is going to be a somewhat nostalgic walk down memory lane. You can see on the right this nice picture from probably the 1960s, which shows a typical human-computer interaction. And the interaction that this young lady is having with the computer is most likely line by line. That is to say, she is going to type some text in successive lines, and the computer is going to process those lines. So a typical program structure for this, expressed of course in today's programming language terms, would be something like this. It's a loop, where each time through the loop we are going to read a line entered by the user. So we assume here a procedure read line which reads a line, a query last line which is set by read line. So after read line it gives us the content of the last line that was read, and also end of file to say if we are finished, a Boolean query. I is not absolutely necessary, it's to count the number of lines that have been read. So each time through the loop we read a line and store the result in this result array. Here of course we could do something else with it. What's important here is that it's the program that is in charge. That is to say, it's the program that decides when input is expected, and the user should enter that input when the program is ready. Fast forward to today. In contrast with the previous 1960s-like line-by-line interaction, we now have a graphical user interface system. It happens to be traffic, the city simulation software that goes with the course and with the textbook, but it could be any modern graphical application with windows, buttons, menus, and other widgets. Now, the fact that it's graphical is not the most important difference. What is really fundamental as compared to the previous 1960s-like interface is that control has changed. control is no longer with the program. It's no longer the case that the program says, okay, now I'm ready to process some input, please enter a line. Now it's the user who is in charge. The user has at every step the possibility of choosing between a number of event types. A typical event type might be left mouse click, so the user can click the mouse. The user can select a button. The user can select from a menu. The user could, of course, type a key on the keyboard if there's a keyboard. And these are examples of event types. And at each stage in the execution of the program, what happens is that the user is going to trigger a certain event of a certain event type. And depending on the event type, a certain action is going to be executed. So it's not now do this, now do that. It's when a user presses this particular button, for example, this preview button here, then execute that action from my program. When the user chooses a certain element from a certain menu, execute that other action. For example, the user could click the mouse. Here we are in a part of the program where we want to find the closest station associated with a certain point. So the user is going to click his or her mouse at a certain point. And when he does that, what we want to do is to find the closest station. So that when user clicks on the map, we want to execute a certain routine from the code, the routine find station, with the arguments x and y, which are the coordinates of the place where the user has clicked the mouse, so as to find the closest metro or tram station. So this is what the kind of interaction that we have today, and it's known as event-driven programming. It's also known as publish-subscribe. So the general scheme is the one that is suggested here. This is going to be a metaphor. You may or may not like it. It may or may not help you understand the concepts. It helps me, so that's why I'm proposing it. On the left-hand side, you have publishers. On the right-hand side, you have subscribers. So publishers and subscribers are software elements. The publishers trigger events, and the subscribers subscribe to events. They're interested in certain events. So the metaphor here is that of a physics experiment where we have on the left-hand side some bombardment of various particles, and then on the right-hand side we see what particles are going to go through the little hole in the screen here. So it's not physics, it's software, but the idea is the same. The publishers are going to publish some events, and the subscribers are going to be interested in some of these events. For example, the first subscriber on the right has subscribed a certain routine to execute for that particular kind of event, and so on. So there might be for that event another subscriber that is also interested in the events of that type, and then for some other events there's going to be some other subscribers, and so on. So it's a metaphor, I give you for what it's worth, but it's the general idea of event-driven programming, also known as publish-subscribe. It's really the same thing, and the general scheme is that some publishers are going to publish events which some subscribers are interested in, and they will execute some operations as a result. There's another way to talk about this scheme. It's to talk about observers and observed. And this will lead us to a program scheme known as the observer pattern. So assume, for example, that we have a certain factory or a certain device whose temperature is being monitored. And then you might, so we call that element the subject, the element or the device or the factory whose temperature is being monitored. And then there are a number of observers which are interested in that value, in particular in changes to that value. So for example, you might have a display which displays the current temperature. You might have a database such that every time the temperature changes, or maybe every 10 seconds, the current temperature is recorded into the database for future analysis or for incident reporting. And then you might have an alarm which monitors the temperature, so that if the temperature goes over a certain threshold, like 40 degrees, an alarm is going to be sounded. So on the left-hand side, we have a subject. On the right-hand side, we have observers. And typically for one subject, you may have many different observers. Now, as you may have noticed, this is very much the same situation as before, just expressed differently. It's really like having publishers, same thing as the subject, which publish events. In this case, the event is going to be temperature change. And indeed, there are several ways to talk about this kind of application and several terminologies that are in use. We can talk about observed and observer, or subject and observer. We can also talk about publishers and subscribers. I will mostly use the terminology publisher and subscriber, but it's not the only possible one. Now, in talking about this kind of application, this kind of graphical user interface application, or I should say user interface application in general, graphical or not, there's a very interesting paradigm which really every software engineer should know about, and every computer scientist should know about. It's the model view controller paradigm, specifically the model view controller pattern, as it's called, or MVC, which was devised by Trygve Renskov, who was then at Xerox PARC as far back as 1979, but it's still very current and widely used. The idea is this. The purpose is to structure applications that involve a strong element of user interaction, graphical or not, and in particular to define precisely the separation between the various levels of the system. So first, we should understand what this MVC pattern excludes. The risk here is to have everything mixed up, to have the program include elements that have to do with the logic of the application, pay people or find stations in our example, or whatever has to do with the actual business logic of the application, to mix them up with graphical elements, elements of control. So a typical business element or model element, assuming that we have, for example, a payroll application, would be pay a person in the sense of computing his or her salary for the month. So that would be in the model. A typical view element would be to display to the person in charge of payroll a screen where he or she has to enter various parameters in order to do the processing. And the controller part is the part of the system that governs what is going to be executed when. For example, when the user clicks an OK button, the salary computation should be triggered. So the mistake would be to mix all these three kinds of elements in the code, and that would be very bad because they change differently. For example, you may want to change the user interface even if the model has not changed. And conversely, if the model changes, for example, if there are no new rules as to how salaries are computed or new taxes or things like this, you want to change the model, but you don't necessarily want to change the view or to change the controller. So what the MVC model tells us is that these three aspects, model, view, and controller, should remain separate. And the picture here, which you can analyze at your leisure, I'm not going to go through the details, there are a few more explanations in the textbook. The picture tells us what the relations are between those three aspects. So for example, the view represents the model. What we present to the user through the view is some representation of the model. The view is there to give us some idea, for example, of salaries and employees and paychecks and so on. So this is an artificial view, it's an abstract view. It's, for example, through a web page, but it's only a view. It's not a real thing. It's not a paycheck. It's a representation of the paycheck or the salary of the employee. So the view represents the model. And so on. The controller is there, for example, to update the view by changing the representation on the screen, but also to update the model. Also note that I've called the view part view sub I, and the reason is very simple, is that for a given model, we may have several views. For example, we might have a text-oriented view, we might have a graphical view, and we might have a view in the web browser if the system is both available through a local terminal and through a web browser. So that's why I called it view sub I, because there may be several different views for the same model and in fact the same controller. So it's really important to distinguish between those three elements, and the MVC pattern is at the basis of many techniques used today to handle graphical interactions. So what we've seen in this first segment of the lecture includes the following. We've seen that program-driven control, in the sense of classical structured programming control structures, does not always work, and that some actions depend on what happens at runtime. Sometimes the ordering of steps is best expressed by letting events drive the execution. Of course, we haven't seen yet how to do this, but we have the general goal. And also, with the MVC pattern, we have seen that it is essential to keep the various parts, in particular the three parts, the model, the view, and the controller, with the understanding that there may be more than one view, to keep them separate in order to preserve evolution of the system.